Hello friends, welcome back. We are starting NMR spectroscopy. So this is one of the very important and useful spectroscopic technique which is known as the NMR spectroscopy. So what is NMR? NMR is nuclear magnetic resonance, and it is a spectroscopic technique because here, similar to UV spectroscopy, IR spectroscopy, this also involves the interaction of electromagnetic light with our sample. Here we use the radio frequency waves. Now this NMR is a very powerful and widely used tool for the structural elucidation or the structural determination. So whenever the synthetic chemist or any particular analyst prepares something, then he immediately rushes to a NMR spectroscopy and he records the NMR spectra for that particular compound, and from NMR spectra we can identify the possible structure of compound. This NMR spectroscopy is widely used to identify the structure of organic, organometallic and inorganic complexes. In addition, these are also used to determine the complex structures like various biomolecules like proteins, amino acids and so on. Looking at historical perspective of NMR spectroscopy, this is a very old technique as it was discovered in the year 1945 by two groups which were working independently, namely the Purcell, Torrey and Pont in Harvard University at USA, and the other group, that is Bloch, Hansen and Packard at Stanford University of USA. Now these group, especially the Purcell and Bloch, has been awarded with the Nobel Prize in the year 1952. So they did a simple experiment with ethanol as a sample molecule which was kept between the two pole faces of electromagnet, and the ethanol was irradiated with the electromagnetic radiation in the radio frequency region. Now it was observed that when the magnetic field was on and the nuclei of the ethanol were exposed to the radio frequency region, there was a absorption of energy or the radiations. However, the moment the magnetic field was turned off, there was no absorption, and this is how the NMR spectra of a simple molecule of ethanol has been recorded. So in today's standard, this is very rough or very unacceptable spectra, but at the first instance in the year 1946, this was a very useful technique, and this was a spectra which was recorded for this simple ethanol molecule having CH3, CH2 and OH protons. So this particular peak, which is most intense peak, was corresponding to this CH3 protons. Then moderately intense peak was corresponding to this CH2 proton, and the least intense peak was corresponding to this OH proton. So this particular NMR spectra was recorded on 30 megahertz of radio frequency with roughly around 0.5 Tesla of the electromagnetic field. Now there are certain nuclei which can be recorded or studied under this NMR spectroscopy, but mainly the nucleus of the hydrogen and carbon are widely studied. So there are basically two types of NMR spectroscopy which are commonly used. One is that is called as H1 or proton NMR spectroscopy. The other technique is C13, that is carbon nuclear NMR spectroscopy. Now whatever discussion we are doing in this particular session, that is restricted only to the proton NMR spectroscopy, and the other technique also have similar kind of mechanism with that of the proton NMR with slight variation. So starting with the theory of NMR spectroscopy, first point is the spinning nucleus. Now as we know, in a molecule we have different sets of atoms, and these atoms have the nuclei. Now when we talk about the nucleus of the hydrogen atom, that is the proton, So this proton behave as a tiny or small spinning bar magnet, and it does so because it possesses both electric charge and the mechanical spin. So we know any spinning charge body will generate a magnetic field, and the nucleus of the hydrogen is not an exception. So in this particular figure we can see this blue circle is nothing but the nucleus of the proton, and this nucleus on its surface it has the charge, and this nucleus has certain spin moment which is indicated with this arrow, and this is spinning around this vertical axis which is indicated with this downward arrow. Now any body which has charge and which has some movement, it will generate its own magnetic field, and this field is called as induced magnetic field. Now the second point is how this nucleus will behave under the influence of external magnetic field. So in the first point we have seen any spinning nucleus with charge will generate its magnetic field, that is called as an induced magnetic field. Now when we expose these nuclei with the induced magnetic field, how these nuclei will behave? Now like all tiny bar magnets, the proton will respond to the effect of external magnetic field, and it will adopt two possible orientation. So what these orientations are? Now consider this B0 is nothing but the applied magnetic field externally, and these are the two possible orientations which can be adopted by the nucleus of the proton. Now there are two possibilities. The nucleus of the proton can align or it can remain parallel with the applied magnetic field direction, and they will remain in the ground state. Okay, because they are parallel to the applied magnetic field, they require less energy. However, the other possible orientation is the nuclei of the proton can oppose to the applied magnetic field, and they will remain in the opposed direction. So this opposed direction is also called as a anti-parallel or the higher energy state. This is called as a ground state or aligned position or parallel position. So usually the ground state nuclei requires lesser energy compared to the opposed anti-parallel or the nuclei which are in the excited state, and this energy difference between the ground state to the excited state is quantized, and this is called as a delta E. So this is the energy difference which is required for these nuclei to shift from ground state to the excited state. Now the next point which is very crucial to understand the phenomena of NMR, that is precessional motion. Now as we have seen earlier, the nucleus of the proton has charge and has spin movement, and this spin movement is around the axis, and this particular spin movement is called as the gyroscopic motion. Okay, so in this animated figure we are showing the gyroscopic motion. Okay, now this gyroscopic motion under the influence of external magnetic field will change from gyroscopic motion to a different motion, that is called as the precessional motion. Now what happens under the influence of external magnetic field? The nucleus of the proton will not only adopt either two possible orientation, but it will also move in a characteristic way, and this characteristic way movement is the change of movement from gyroscopic motion to the precessional motion. So what is precessional motion? You can see in this particular figure, the precessional motion is similar to the movement of the rotating top. When the top is about to fall down, it will perform slower wards like motion, and this slower wards like motion is nothing but the precessional motion. So that is slightly different from the gyroscopic motion. Okay, so the precessional motion orbit is little bit larger compared to the gyroscopic motion. So this is exactly how the precessional motion can be understood with this particular animated figure. You can see earlier it was moving exactly around its axis, and that was a gyroscopic motion. But under the influence of external magnetic field, it has changed its spin movement from gyroscopic to the precessional. Now what is this precessional frequency? So this is nothing but the spinning frequency of a particular nuclei per unit of time. Now what we can understood, the precessional frequency is fixed, but the speed at which it is going to precess, that can be changed. So this particular precessional frequency of a nuclei is directly proportional to the external magnetic field. Now this precessional frequency can be indicated by this nu, and this nu is directly proportional to the B0. So B0 is nothing but the external magnetic field strength. Now to understand this in a better way, we can consider we have a nuclei of a proton. If they are exposed to the external magnetic field strength of 1.4 Tesla, the nuclei will precess at frequency 60 million times per second. In short, it is a 60 megahertz. So what we mean to say, as we are increasing the external magnetic field B0, the precessional frequency is also going to increase. Here, instead of 1.4 Tesla, if I use 2.3 Tesla external magnetic field, instead of 60 million times per second, now it is changing its frequency from 60 to 100, and so on. Okay, so this is a simple theoretical equation which indicates the nu is directly proportional to the B0. Now next point is the energy transition. So as we have seen, the proton is capable of taking two possible orientation with respect to its axis under the influence of external magnetic field, which could be either parallel to B0 or it could be a anti-parallel to the B0. Now if it is taking aligned orientation, it can absorb energy and pass into the opposed orientation, and when it goes into opposed orientation, subsequently it need to stabilize by releasing the extra energy what it has gained, and it will come back into the ground state. Now if I am irradiating, if I am exactly knowing what energy frequency it requires, that is a delta E, and if this delta E I match with the correct radio frequency wave, now what I can do, I can bring the nuclei in the ground state into the excited state. So this can be understood with this particular diagram again. Now let's say I have the nuclei in the ground state, and these nuclei require this delta E. This delta E is a quantized energy, it is a fixed energy required by this particular set of nuclei to move from ground state to the excited state, or to move from the aligned state into the opposed state. Now this delta E, if I provide externally with the help of radio frequency beam, what will happen? The ground state nuclei will shift from ground state to the excited state, and this is how we can bring the nuclei into the resonance. So that's why the name of this particular spectroscopic technique is given as nuclear magnetic resonance spectroscopy. We are using the nuclei, we are using the magnetic field externally, and we are bringing the nuclei which are in the ground state to the excited state by providing the quantized energy with the help of radio frequency beam. So this is basically the principle of this NMR spectroscopy. Now how exactly the NMR spectra look like in today's standard? Now this is an ethanol spectra what I have represented in this particular figure. Now here at 0 scale we usually consider the internal standard peak, that is the TMS, and with respect to TMS we plot our all other proton peaks. Okay, so we'll discuss this in detail in the coming slides. Now again we can see the CH3 or methyl protons are the most intense peak here, that is having 3 protons. Then we have the moderately intense peak, that is CH2 proton, and then we have the least intense peak, that is the OH protons. Okay, so by looking at the particular spectra we can get the information about the structure of the compound and how many protons does it have in a particular structure. Now, to understand the NMR spectroscopy in a more better way, we are considering here the nucleus of the proton. That means the nucleus of the proton is NMR active. It is capable to absorb the energy through the radio frequency waves. Now, what nuclei are NMR active? So, only those nuclei will exhibit the NMR phenomena which has the spin quantum number greater than 0. That means if any nuclei has the spin quantum number 0, then it is considered as it is NMR inactive. We are not able to record the NMR spectra for such type of nuclei. Now, this spin quantum number is abbreviated as capital I. Now, this spin quantum number depends on mass number and atomic number. So, mass number is the number, that is total number of protons and nucleons in a particular atom, and atomic number is the total number of protons in a particular atom. Now, if mass number is even and atomic number is even, then the spin quantum number I will be 0. So, we have an atoms carbon 12, oxygen 16, sulfur 32. All these atoms will have the spin quantum number I, that is 0, and hence we cannot record the NMR spectra of such atoms. When your mass number is odd and atomic number is even, then the spin quantum number will be half integer. And the best example of these half integer spin quantum number is H1, F19 and phosphorus 31. Then we have the other atoms that you can overlook it. Then the most important for us is H1, and I have told you C13 is also widely used. So C13 have even mass number and odd atomic number, and that also has the half integer. Okay. Now, how to find out what are the possible orientation taken by the magnetic nucleus under the influence of external magnetic field? Now, when we talk about the proton, the spin quantum number is half, and there is an empirical rule to find out this possible orientation of the magnetic nucleus, that is 2I plus 1, where I is the spin quantum number. So for H1 we can find out easily with this empirical formula what are the possible orientation by this particular nucleus. Now here 2 into I is half plus 1, so that will come 2. So that means the nucleus of the proton under the influence of external magnetic field can adopt two possible orientation. So what are those two possible orientation? One is a ground state and other one is a excited state. Then next is a gyromagnetic ratio, or it is also called as a magneto-gyric ratio, which is a very important parameter in the NMR spectroscopy. Now in an applied magnetic field, the magnetic nuclei like proton, they will precess at a frequency nu, which is proportional to the strength of the applied magnetic field. Now to be very precise, this precessional frequency nu is equal to the gamma into B0 divided by 2 pi. Now B0 we know it is a strength of the applied external field experienced by the proton, and this gamma is nothing but a magneto-gyric ratio or gyromagnetic ratio, which is a ratio between the nuclear angular momentum divided by, it is a ratio between the nuclear magnetic momentum mu divided by the nuclear angular momentum I. Now again we can have the relationship between the nu and the applied magnetic field. So for example, for H1, if I am taking 1.4 Tesla B0, then the precessional frequency is 60. Now as I am increasing from 1.4 to 1.9, the precessional frequency is increasing. Okay, so you can see here we have given in a tabular way in an increasing order from 1.4 to 14.1 Tesla as a applied magnetic field B0, and here you can see in this table for all these nuclei which are NMR active, the precessional frequency keep on changing, keep on increasing with respect to that of the applied magnetic field. Now when we talk about the sensitivity of the NMR, the strength of the signal and hence the sensitivity of the NMR experiment for a particular nucleus are related to the magnitude of magnetic moment, that is mu. Now the magnetic moment of proton, that is H1, and fluorine 19 are relatively larger, and that makes the wide use of this proton and fluorine 19 NMR spectroscopy, which is used very widely to interpret the structure of the compound. But we know most of the molecules does not have fluorine atom in its structure, which makes it is less useful for a particular set of compounds. However, we have the lot of organic compounds in which we have the proton, which is very abundant, and that's why the proton NMR spectroscopy is very widely used to elucidate or to interpret a particular structure of compound. Now next point is the energy transition and the relaxation process. Now consider if your proton is absorbing 60 MHz radio frequency and it is going into resonance. So what does that mean? You have the protons which are in the aligned position under the influence of this B0, that is external magnetic field. Now this requires this delta E, that is quantized, and if you are providing the correct radio frequency and you are bringing them into the resonance, that is shifting these aligned protons into the opposed protons. Now when it goes into opposed orientation, that is they are going into resonance, now immediately they will come back into the aligned position. They want to get stable. Now when they are coming back into its original position, they releases this extra energy which they have gained from the radio frequency beam. Now that is how the nuclei will going to relax. Now for relaxing these nuclei, they have to release this energy and they have to transmit this extra energy to the surrounding nuclei. So this can happen by two ways. One is called as a spin lattice relaxation, or this is also called as a longitudinal relaxation. Now if the nucleus which is surrounded by the neighboring atoms or the solvent molecules, now if these solvent molecules or the neighboring atoms, they are orienting themselves to gain this extra energy which has been loosed by the particular nucleus, and if energy transition happens, then that is called as spin lattice relaxation or the longitudinal relaxation. The other one is a spin-spin relaxation, or it is a transverse relaxation. When both nucleus require same energy, then one nucleus mutually exchange its energy to the other, and therefore no net change in the population of the spin state will be observed, and this is called as the spin-spin relaxation or the transverse relaxation. So this is all about in part 1 what we need to discuss. So we'll come shortly with the next part. Thank you all of you for watching.